by the way. Yes. So it's always, and it's periodic if there is, because you see a period is if you shift, then you keep the same configuration. Of course, if you shift by 0, you keep the same. So for every configuration, you have 0.
You cannot shift.
But you will not say that the configuration is periodic. You will say that it's periodic when there is at least one non-trivial vector.
Oh, well, and then what is the matter with finity?
So for example, you have this is a setting that is relevant also if you replace V2 by any group. But in V2 it's simpler. In V2,
well, it's kind of understandable.
In V, you understand that there is one notion of periodicity. Because the vector has to be in Z. So if you are weakly periodic, then but in V2 you have more or less two notions, because you can have a configuration, for example, let's say that I have two states, white and blackboard. Okay?
Yeah.
And if you have an infinite line of white and the rest is only blackboard, then you have a non-trivial vector of periodicity, which is 0, 1. Okay? If I shift, if I go up, I see the same configuration.
Yeah.
So it's a period.
Yeah.
But it's not still, when I look at the set of all possible shifts, I have infinitely many of them, because I can shift horizontally and put the line wherever I want. And the second notion of periodicity is really, strong periodicity is really something where you have something where you have periodicity in the two directions, horizontally and vertically.
Oh, yeah, that's, now I understand.
So the finite index means that literally it means that you have finitely many cosets in a subgroup, because this is always a subgroup of these two. So was this the first question? Yes, I'm sure that it's a normal subgroup of the two. So the subgroup means that if I have P and Q that are in this, then P plus Q is also in this, and minus P is in this, okay? Minus P minus Q. This means it's a subgroup, and I didn't prove that it's I didn't prove it. Actually, I'm just explaining what it means. I didn't say what it means to be a normal subgroup, but to have finite index means that if you take the set P Z2, K plus ST of X, and this is finite. So for example, here, imagine you have ST of X. So you have one vertical vector periodicity, let's say 0, 1, and you have one horizontal vector, maybe not even horizontal, maybe vector 2, 2, 1. So 0, 1, and 0, 1, and 2, 1, maybe. So these are rectangles which are more have 0, 2. 0, okay, it's not a good drawing then. 0, 2, and 2, 1. You have two vectors of periodicity, okay? Then you can see, since it's a subgroup, actually, if you add this vector with this vector, you arrive here, and this is also a vector of periodicity. Because if I shift like this, I really see again the same configuration. If I shift like this, it's like having shifted like this at the beginning, because it was the same configuration. And here I know it's a bit vector of periodicity, so it's again the same configuration. So you have some kind of grid of the vectors of periodicity. This is how we represent a subgroup of D2. All of these points are vectors of periodicity. Okay? And and now if I look, so ST of X is more or less this grid. Okay? And K plus ST of X is shift of this grid. So for example, 0, 1 plus ST of grid, ST of X, vector 0, 1 plus ST of X is a grid which is exactly parallel, but you shift it by 1. So it's a different grid, okay?
Yeah.
But then if you take 0, 2 plus the grid, you shift exactly by the size of the vertical thing, so you get exactly the same grid. You agree?
Yeah.
So,
it's periodic, so yes.
yes. And of course, if you take K, which is inside ST of X, you have, so I didn't, so you understood that this means K plus the set of K plus P for P and ST of X.
Yes, of course.
So here, I have a set of sets, okay? These sets are grids, and I look at the set of all the shifted grids. And what I'm saying is that there are only finitely many of them, because you can try to shift your grid, but if you shift it by something which is by any vector which goes into this parallelogram, here, I don't know, maybe, so maybe you can count them. There is 0, 1, there is 1, 1, 1, maybe 1, 2. And there is 0, 0. So you have 4 different grids which are parallel, but if you take any other vector, if you take any bigger vector, you can always find a vector of periodicity which makes you come back in this parallelogram. So actually the grid is the same as one of these 4. So in this example, you have exactly 4 parallel grids. I'm drawing on stupid example with squares, but if you take this example and you draw what the grid looks like on a sheet of paper with small squares, you will understand that you can try to shift and you have exactly 4 parallel grids, or maybe some other number because I made a mistake, but at least a finite number. So, So yes, so this is finite index, because the set of cosets of a subgroup, the set of cosets of a subgroup is exactly the set of different shifts of this subgroup. You understand that when I say shift, here I shouldn't say shift, I should say maybe translation. It's not the same as shifting of configuration where you have colors on each point. Here I just translate some set of D2. So So forget about the word shift I use several times. We translate. They are essentially the same thing. So the set of cosets the same as the translations of the grid, which are different. So in the first example, we have only one vertical line which is different, and the rest is equal. Then of course, then the subgroup ST of X is not a grid, it's just
A line.
yes, maybe sometimes not, yes, it's the set of all vertical vectors. Sometimes you can have a vertically periodic configuration with period 2, and then you have a subgroup of the vertical line, but at least it's not a grid, so you have infinitely many translations of this subgroup, because you can put this line everywhere on the group, so it doesn't have finite index. So this is why we say weakly periodic and strongly periodic. And at the end of the exercise, I think I ask you to prove that in the case of Z2, this definition with finite index is the same as having a vertical and a horizontal period. No.
False? No?
No, it's the second question.
Yeah.
The second question, you see that in Z2 it's the same as having a vertical and a horizontal period, which are non-trivial, because as soon as you have them, then the subgroup generated is some kind of grid, and you see that you have some fundamental domain on which you can find the representative of every coset.
A tree of fact, but the suburb is not, it's a good group.
Yes, that's why I said deduce. I asked you to prove that it's a normal subgroup, and then I said deduce this. I agree this is, when you know about group theory, it's quite easy. I agree. It's not as difficult as many other things that we did. I don't know, do you want to go further into this exercise, or?
No, we can switch to the next. I at least have now the understanding of all basics needed for this exercise.
So, but first, you understand that when we speak about one dimension and we say that something is periodic, everyone agrees. You don't even need to really define everyone will see what you mean. But in two dimensions, there could be two different notions. A weak one, where you say just, okay, if I shift by something, I see the same thing. Or a strong one, saying that I can shift by many things, I will see infinitely many pictures. When you replace D2 by groups, you have these different notions but when we talk about SFT, one of the questions at the end is to prove that actually, if you have a weakly periodic configuration in an SFT, then you have a strongly periodic one. This is not true at all, and it's not true if you replace Z2 by Z3. But in Z2 it's true essentially because when you have one period, you remain with just one other dimension. In some sense, you take a configuration with one period, and the complementary dimension is just one. But an SFT, it's very vague what I'm saying. It's just the intuition. then you remain with some kind of SFT in dimension 1, and we know that these are very simple, and they all have a periodic configuration. So,
and why it would be not so in V3?
Precisely because of what I've just said, that if you have one vector of periodicity, then you remain with two dimensions, and you have much freedom. So in some sense,
so we have SFT even if we have one vector of periodicity, not two.
So, yes, so.
How would it be strong?
No, it will not be. What do you mean strong? Strongly periodic?
Yes.
So yes. So in 2D, if you have an SFT which has a weakly periodic configuration, then it also has a strongly periodic configuration, because you can concentrate on this. You can look at this you can look at this weakly periodic configuration, and more or less its orbit looks like a one-dimensional SFT. And we know that one-dimensional SFT are simple and admit periodic configuration, so you get a period in the other direction, and you get a configuration which has two periods. In 3D, if you have one vector of periodicity in a configuration, you look at this configuration, and it looks like a two-dimensional SFT, and so it can still be very complicated, because we know that two-dimensional SFT can be very, very complicated. In particular, if the two-dimensional SFT is L-periodic, then you get an SFT with a weakly periodic configuration, but with no strongly periodic configuration in 3D. So maybe I didn't state it exactly like this in the exercise, but you can, yes. Yes, maybe we. Let me rephrase one of the questions. Maybe question 4. Another hint than the one I gave. Question 4 of exercise 4. I don't care, I just say vertically to be able to operate, but you...
Doesn't matter.
Periodic. So just a weakly periodic configuration. Then the orbit of X by the shift can be seen as let's say the orbit of X by the horizontal shift can be seen as one subshift included in one SFT is itself completely in X. So here, there are two informal statements, but you can formalize them by taking the as an alphabet. So you can formalize them by taking the trace of the subshift. If you take tau of y equals y I 0p okay, I have a two-dimensional configuration, and I take the trace which corresponds to exactly to the period. So here, in my first example, which now looks like just a separation between. So let's say that I have periodicity vector 0, 2. I take a stripe like this, which corresponds to my vector, and I take the whole stripe.
Yes.
And this, since it's a bounded stripe, I can see it as a configuration, a one-dimensional configuration over an alphabet which is the power of the previous alphabet. This is in A to the P to the Z. Here I have a one-dimensional configuration, but P symbols one on top of the other at each place. And what I'm saying here is that I take the orbit of this x, of tau of x, and then there is an SFT which contains it, such that the unfolding of the tau admits an inverse tau minus 1 over periodic configurations. Do you agree that there is only one way to recover the original configuration?
Yes.
And for every possible word that I obtain like this, there exists tau minus 1. What I'm saying is that there exists one-dimensional SFT. So this is the formalization of this intuitive idea. There is a one-dimensional SFT. Give me a letter. Z. Such that tau of y is indeed Z. And Z and tau minus 1 times of z giving x. So this is a set of periodic configurations. It's not very hard to show this, but once you have this, you know that in one-dimensional FFT it's not empty because you have at least one element. So there is a periodic configuration, and when you take tau minus 1 of a periodic configuration, you get a strongly periodic configuration because you keep the horizontal period and you add a vertical period.
So let's say we are in our one-dimensional SFT have an alphabet of 0, 1, and we have 1 in the middle and it goes to the infinity on the side of 1, and we count it as periodic. Like that. We have, for example, here we have 1, and then we have 0, like that. Yes or no?
Yeah, yes. Okay, in this example, yes, essentially you take tau and you have this, okay? And then you know that it will be, so because of the fact that X is an FFT, you know that there is an SFT containing this, maybe of bigger size, but actually it's not difficult to see it. It has the same size, which contains this, and whose unfolding by tau minus 1 is included in X. So it has a periodic configuration. And this periodic configuration, you can see it because you just have to shift with many zeros. In this case, in this particular case, you don't even need this. It's really trivial that you see that when you shift to the infinity on the left, you have a configuration with only zeros, which is periodic in both directions.
But we will eventually see a 1 on the right if we shift left, something like this. No? Well, for example, let's say we are not in here, but in there. Yeah? How does it work?
No, this doesn't change.
Well, but there is no periodicity here.
There is no periodicity, there is no horizontal periodicity here, and here it's nearly the same configuration. Here you just have a vertical period, and you don't have horizontal period in these two configurations. But what I'm saying is that then if you shift infinitely many times to the right, you have something with a horizontal period. And then in this shift you actually have something with two periods. And when you periodize, you obtain one configuration like this, which is periodic, horizontal, and then you unfold it, you put it periodically, vertically, you get something with two periods. In this case, it's quite trivial because we can see it directly in the orbit closure. So it's not only that we didn't even use the fact that it was an SFT in this case. But this argument remains true if you are not in the subshift with only one vertical line, but maybe many vertical lines, only vertical lines of white or black, and the vertical lines are placed in a way such that you cannot extract periods directly. So in the orbit closure of such a configuration, there may not be a doubly periodic configuration, but in every SFT which contains this configuration, you can extract the periodic configuration. If you don't want to see it as a one-dimensional SFT, you can also directly do a pigeonhole argument on. It's the same.
Okay.
Do you want to go through more deeply into the? Sorry, yeah.
Have anyone else have other questions
About?
About anything, or I will continue asking.
Do you have questions also?
Not yet.
And you?
I can ask a question about this exercise. Okay, if you know that, but we have just explorations input in this question, yes? So to know that it's contained its like orbit closure, and how do we know that an orbit closure is contained in some SFT?
Then you have to use that we are in an SFT, because it's not true in an arbitrary subsheet. It's not true that when you have a vertically periodic configuration, you may have a double periodic, but in an SFT it's true. So you use that you are in a two-dimensional SFT to prove that, and you explain what it means for the trace. But there are several ways to see the same argument. There is also, you can also okay. First, one very important thing for this kind of proof. What do you know? So you can simplify the thing that you want to prove. Because when I say SFT, you know that there is a way to describe SFTs which are easier than dealing with lists of finite patterns.
We can talk about language of it. Of a shift of the SFT.
Yes, but this is not easier in the case of SFT because this is definitely not easier, especially in two-dimensional SFT, because the language can be very, very complicated, even if you have finite list of finite patterns. But I'm talking about a very simple transformation that we saw. If you have big patterns that you forbid, for example, you know that they are bounded. You can re-encode your SFT as a nearest neighbor subshift. So, and this conjugacy, the conjugacy that is involved, preserves the periods. Conjugacy always preserves the periods. So, typically, what we want to prove, we can prove it on nearest neighbor subshift, and it will derive directly for SFT. Maybe, I don't know if this is, sometimes it helps to see how it works, but if you don't do this, you can also deal with a block, a size of block where you know that all of finitely many constraints will be encoded in this block of forbidden patterns. The forbidden patterns all have a size which is included in this window. And so what I'm saying now, imagine that you have a n times m block size of block, which includes all finite constraints, all finite patterns. Then, in the trace, you can prove that if V is in the approximation SFT of length m of tau so let X hat be the set of vertically p-periodic configurations in X. So our assumption is that this is not empty. And AM, I will recall what it is. AM is the set of configurations which look like a configuration of tau of X up to patterns of length n. So this exactly means that the language of patterns of length m in Z is included in the language of patterns of length m in tau of X. So all patterns of length m in Z appear in some configuration in tau of X. If I want to show that then Z belongs to tau of X. You remember, this is the way of showing that something is an SFT. To show that something is an SFT, you have to have a candidate of window, of size, of order of the SFT, okay? When you have this candidate, here I take it directly from the order of the two-dimensional SFT. But I forget about the vertical part, because basically in the trace we have the information about the whole vertical stripe, but we don't have the information about the horizontal. Yes. The whole vertical stripe is encoded locally because we deal only with periodic configurations. So I take the horizontal part of the order, and I'm saying, okay, maybe if I glue locally valid patterns next to one another, and I build any configuration like this, maybe it's still a valid pattern. And this, if you prove this, you exactly proved that tau of X is an SFT. Then if it's an SFT, it contains just one-dimensional SFT, so it contains a configuration which is periodic, which means that tau of X contains a configuration which is periodic, and it must have a pre-image by tau, which is horizontally periodic and vertically periodic. So I don't know if you want me to. I think it's not so difficult at the end to prove this. Maybe you can finish at home.
question, but not to the exercise. It's a bit a general abstract one. Some constructions that we were looking at, like definition of SFT or constructions of subshifts, they are similar in some way to constructions of algebraic geometry, like using ideals to construct points.
You're talking about the exercise with the triangle thing, yes?
Not about exercise, but
there is one exercise, especially on this algebraic geometrical aspect.
Which one?
One exercise.
Okay.
The one with the exercise 5.
Okay.
So we define a subshift as an ideal of this algebra which is defined by yes, you can understand the configuration. Do you want to talk about this exercise 5?
Yep.
I think I helped you enough. So in exercise 5, yeah, typically we are interested in this type of configuration. Over 0, 1. So you have a 0, 1. How does it work? 1, etc. So what I'm doing is that all of these triangles, all the triangles with this shape, I put them everywhere on the configuration, and I do the sum modulo 2, and I should always get 0. Okay? This is a natural condition. Do you understand that it's an SFT? It's an SFT because locally I just need to look at this shape everywhere to show that it satisfies this condition. And so now this is configuration X. So usually you understood that often I use this notation Xij, where ij are in V. Okay? And this configuration can be seen as some kind of bi-infinite Laurent polynomials. So formally I can write sum of the xij, x to the I, y to the j. So now I haven't done anything, I just wrote it differently. I mean, this is very formal, it's just, the only thing that I've done by writing it like this is suggesting you to consider a multiplication between such objects. maybe not a multiplication between two such objects, but a multiplication between such objects with a polynomial. If I have polynomial P equals 1 plus x plus y,
even multiplication of both series is well defined, so it's okay.
Then you would have some.
For each term, there is a finite number of sums that define the result.
So this is true when you have Laurent series, but here Laurent series. Sorry.
Which series?
Laurent series. Laurent series, in general, you can have it will correspond to a configuration which corresponds to the timing of the quarter plane. But in the timing of the full plane, I don't see why you have only finitely many coefficients.
Okay, yeah. No.
If you have a bi-infinite, this is why I insisted on bi-infinite Laurent series, because it's not a general term. It's quite natural to transform this into this, but it hasn't been, it's not an object that comes from other topics, but it's quite easy to multiply by a polynomial or by even by by a polynomial. So if I multiply, let's say this is, okay, let's say this is x again, and I multiply p by x, and I get, for every coordinate, I get xij plus xi, so maybe let's put it like this. It's not really a polynomial. What's the example I put? I put xy plus 1 plus x plus j. Yes. I think.
First inverse of y and plus xy. X and inverses of x to minus first power and y to minus.
Okay, maybe it's not what I meant. Maybe this is an error. Because sorry, okay, this is, I mean, maybe this is interesting, but maybe what I meant is just this, or equivalently, maybe I hesitated too much between two variants. Q of xy equals 1 plus x minus 1 plus y minus 1. So let's do it with this, and I hope I will correct. Then x plus 1. So at each position ij, I get the coefficient of I plus 1 j plus 1 plus I j plus 1 plus I plus 1 j. No? So I think I again got it wrong. Yes. So all the plus 1 or minus 1. Do you agree?
Yes.
So if I say that should be 0, this formal Laurent series should be 0. It's the same as saying that for all ij, xi minus 1, j minus 1, plus xij minus 1, plus xi minus 1j equals 0. I'm not saying modulo 2 because it's implicit because we are in d over 2, okay? And actually you can see that it's exactly the same if I had put Q, I get the same conditions, except that everything is shifted. Because P is this one and Q is maybe this one, but since we are requiring this for every shift, it's the same. This is where I made the mistake. I'm sorry for the mistake.
How does the window you draw connected with polynomial?
It's it's actually the symmetric. Because you see the error that I made by replacing the plus ones by minus ones is precisely because here I have so the coefficients that I get here are exactly, so here if I have ij, here I see I minus 1, j minus 1, plus ij minus 1 plus I minus 1 j, and they should add up with 0.
Yes.
And these positions can be seen as symmetrical with respect to the powers that you see here. So in some sense, the polynomial, maybe the polynomial has this support, in some sense, and you're looking at, you want to know all the positions. If you are in position ij, you want to know all the other positions, such that when you shift this, you are in the support of this.
I don't understand. Well, if we shift our first triangle by a layer up, we will get 1 where we had 0, and how does it correspond to that?
Yeah, such a window will be a coefficient for some formal term.
Do you understand that this triangle corresponds to this position?
No, I don't understand that.
Okay.
For example, if we have this one, yeah, we have 1 but not 0 here, and well, where do we have even the idea of it in the first place?
We pick some position and look at other positions that are besides to it, near to it, and we want the sum of these nearest positions to be equal to 0, because we know that the formal bi-infinite formal series, Laurent series, is equal to 0. So we express it we find the connection between the configuration in its graphical expression and the formal series. So we can take any position, and when we multiply by the polynomial of this form, we look at 3 nearest points to some given point, and look if they sum up to the 0.
Oh, yes, thank you.
I'm not sure if it helps you.
You understood?
Yes, it helps.
So for every position, ij, here I have the sum of I minus 1j I minus 1, j minus 1, I, j minus 1. And the condition is that there should be 0. So the
But we can
annihilation of this product is exactly the condition that I described at the beginning, that in every triangle they sum to 0.
Yeah, but we only can have triangles that are oriented this way.
Yes. It's very important that they are oriented this way. That's why this was misleading, because I'm just saying that, in some sense, this is the support of this polynomial. You see, if you see the coefficients here, 1, 1, 1, 0, and 0, 1.
So the other triangle corresponds to the other polynomial, 1 plus x to minus 1 to plus y to minus 1. The other triangle.
Yes, and this is the same support as this one, but shifted by 1, 1. So that's why I'm saying they describe the same thing. Because and the support of this polynomial is always the symmetric of the final window on which you're describing the thing. Because of this, because when you do the product by involution, if you write formally, you get this. In some sense, here I'm trying to say again the sentence I tried to say. And this triangle is the set of points on which if I center a triangle on this point, then I contain this one. So maybe it's easier to see it like this. So if I center a triangle like this here, then this one is inside. If I center a triangle here, then I am also inside. And if I center a triangle here, I'm still inside. So these are the three possible centers of this support for which this particular cell is inside. I'm rephrasing the fact that we're taking the symmetrical. And you can define an SFT. If your alphabet is, let's say, field, then you can always define an SFT by any kind of polynomial like this. Okay, and
why do we do it like this? Well, we have some row of the zeros and ones in the beginning, and why do we sum them like this? How do I get it from here?
It's just an example of SFT.
So it's a random example. Or not so random.
You mean the example of SFT, or you mean the example of configuration?
The example of, well, how do we get second row?
So,
I understand.
I think you're getting into the question. I think, but it's true that to put an example of configuration, what I did is to draw one line, and then...
Well, the line was random.
Yes.
That's understandable. Why do we do the second line this particular way?
To have shapes equal to sum of shapes equal to 0, to have polynomial equal to 0, series equal to 0.
So that's why we do it this way.
Yes, I just want an example of configuration which is in the SFT, XP, where XP is defined by the set of configuration whose associated by infinite Lorentz series is annihilated by polynomial P. So
we can take some other way if it gives us 0 in the end.
I think it will be
unique way.
As long as you write some string, there is only way you can write down what's, or maybe not unique, but
well, that's the question, whether it is unique.
I think that's one of the questions in the exercise.
Wow!
If you take a line, if you take one line, how many possible ways to fill the next line? So, for example, I just have one line. What's the possibilities to have? Don't look at everything here. I just know that I have one line like this. What can be the letter here?
So that we have 0.
At least 2 ways.
Well, yeah.
White way.
At least 2, because we can just write at random, pick some point, some position, and write a random number to the up, and we have already defined to the right number and the left number. But maybe for other shape, yeah. For other shape.
Like for this shape.
For this and.
For this shape, for example, let's not forget. Okay, I have tiled here. How will I continue to tile upwards?
So we only can have one in the first place, because if we have put 0 there, then the sum would not be 0. Yeah, I understood.
And then?
1, 0, 1.
Yes, and actually, if you look at these two things, you do the sum modulo 2, and you take the inverse, the opposite, it's equal, because we are on V2, and it should be here. So you have a local row, which from 2 cells here give you the states that you have to put here. So it's an example of cellular automaton. We are in the space-time diagram of a cellular automaton.
Yeah, sorry, it was a stupid question.
No, you're saying that my exercise is stupid?
No, my question was
But it was one of my questions.
No, it was.
So you're saying that my question was
no, it shouldn't be.
No, I think it's more or less one of my questions, so it's not stupid.
Yeah?
So it's very, very smart. I mean, what is stupid is that you haven't read it, that none of you have tried to solve it before asking it here.
Probably.
But otherwise, if you come up with this question without having read the things, then it's a good
I
question.
probably can't even understood that it's put here.
Because maybe it's not exactly the question, but it's hidden somewhere.
Well, that may be so, but I can see the question I asked him here.
It's in question 3. It's question 3.
So how do we prove?
Oh no, I can't understand.
Remember what I talked about space-time diagrams of cellular
Yes.
It's exactly space-time diagram of cellular automaton exactly means that when you can fill a line in any way, and then the next lines are determined by a local rule from the previous line.
What is surjective cellular automaton?
And surjective because...
What's just the definition of surjective?
Surjective, remember that cellular automaton is a map from some A to the G to itself.
Okay, so the image of
So the global map should be surjective, not the local map, of course. We have S in A to the Z itself, defined by S of X for some local rule S and some R, some radius R, okay? And why am I saying, why am I talking about surjective cellular automaton? So I want to look at space-time diagrams of such things. What does it mean, space-time diagram? It means that I have a configuration, a two-dimensional configuration, and each line is an image of the previous line that is just below it.
So if to rephrase, if we take for any state, we can consider this as a final state, and it can be obtained from some initial state.
Sorry, I have a terminology problem. What do you mean by state?
Just
the configuration. Okay, let's.
Okay.
I mean, it's not the. I don't care about the. We could have chosen another word from the beginning, but maybe it's simpler for everyone.
No, if we speak about automaton, it's usually some state.
So a state in a cellular automaton usually would be a symbol of state.
Okay.
In cellular automata or even finite automata, usually state makes people think of something finite. And the infinite thing is configuration.
So we can go to any configuration starting with some configuration. That means it's surjective, and it also means it's bijective.
It also means it's bijective?
Bijective.
I'm not sure.
Bijection, so one-to-one correspondence between initial configurations and ending.
So for example, what is the cellular, I said there was a cellular automaton here. What is it? So what is the R and what is the F?
F is
maybe first R.
R is 1, and F is some modular 2.
So we ignore the left.
Yeah.
Okay. So, okay, we have a cellular automaton. Okay. And what is, so we said that if the cellular automaton is bijective, then there is an inverse map.
Yep.
And by compactness, the inverse map is even a cellular automaton. So if you think that this is bijective, maybe you can come up with the inverse map. Or maybe you can, sorry?
Is there inverse map?
Is there an inverse map? But if it's bijective, there is an inverse map.
So it's not bijective. Because if we go down, we have two possible configurations for zeros and for ones. We can
For
have, when we have 0, we have either 2 zeros or 2 ones, and when we have 1, we have either 0, 1 or 1, 0. Well,
So give me two valid rows.
well, like this. 1, 1, 0, 0.
Are you sure that it can be extended?
Yeah, I'm pretty much sure. 1, 0, 0, 0, 0, 0, 0, 1,
Then you
1, 0, 1.
Then you don't have any more choice.
Why not 1, 0, 1, 1? I can extend it to how much I want.
What you did, you have a choice here,
And
but then you don't have any more choice.
yes, but I have 2 rows anyway, because I will have them exactly like this. Like, I don't even care. They will be exactly opposite.
Okay. So do you?
We have 2 configurations.
Yeah, I thought the bijection, subjectivity and bijectivity was about not small f, but about large f. So, yeah, then I agree.
Yes, it's about capital F. Capital F is surjective but not bijective.
Okay.
It's not bijective. I think you have to prove it. But we didn't yet prove that it was surjective. Maybe you can do this at home as an exercise. Okay, so there is determinism upward, but not downward. But you understand why it's important to have surjective cellular automaton? Because I want, still, there is at least one possibility to go down. If I don't take a surjective cellular automaton,
There can be no pre-image of sound.
maybe I start with a line, yes, and I cannot go down. And then, maybe I should not consider this configuration, but it's another definition, but at least the space-time diagrams, by infinite configurations, they do not take into account all configurations. So surjective implies for all x in A to Z there exists, maybe we'll call it Z, there exists x in xf. So xf is the two-dimensional SFT associated to f. Let me recall for sake what it means. It's the set of Zi okay. Set of x such that this is the ith line dynamics. I put x index I, x in A to the Z squared. Okay? So if I put only one index, and xi is just a line. So this is the SFT. This is a set of lines the set of sequences of bi-sequences of lines which respect f. And this set we saw that it's an SFT. It's not difficult to prove that it's an SFT. So what does surjectivity imply on this set? Implies it's not empty, but actually this set is never empty. Many things imply that it's empty. It's much more than this. It's more than. So what did we say before?
It means that you can go up only one way. Well, there's only one way to go up.
Okay. So this is the case for every subshift built from a cellular automaton. Even if it's not surjective, this subshift. And what does surjectivity imply? So what is surjectivity? Tell me the definition of F being surjective.
That image coincides with the whole subshift.
Yes, sure. So set differently for every
configuration there is a preimage.
yes, for every configuration there is a preimage. So that's more or less what we did here. For every I write any line, and I can find a preimage that I can write just below. And then I can also write a preimage just below, and just below, and just below. So, maybe by compactness. No. You don't need compactness, but by induction you can prove that every line, every possible line of the full shift randomly appears in one bi-infinite sequence like this, a bi-orbit of X.
Is there a way that we don't have a preimage?
Yes. Example of cellular atom which is not surjective. So I'm using sorry, I'll go back to this question in just 1 second. But here I'm using the tau that we've seen before, the trace, the horizontal trace. So the horizontal trace of XF is the full shift. The horizontal trace is included in the full shift by definition, and for every configuration of the full shift I can extend it upwards, because by definition of the orbit of a cellular atom, and I can extend it downward because it's surjective. I can always extend it. So I have this. Maybe now an example of cellular atom which is not surjective. I think you can come up with one.
Types 1?
Yes. Yes, okay.
Some constant here.
Okay. Maybe a little less trivial, maybe? You have an idea?
It's not trivial for me, because if we have some rule which gives us the row up,
It can be a constant rule that for any row it gives some predefined row upwards. And if we take the preimage of some other row, it will have a preimage.
Okay, look. Imagine your local rule always gives you the letter 1.
Yes.
So do you agree that the global rule always gives you this?
Yes.
So what is the set of possible orbits? What is the set of stylings that you can build like this?
Why wouldn't it give me 1 if I go down?
Yes, it can be 1 if you go down.
So I'm happy image with all 1s. So how can I don't have happy image?
You consider rows that consist not only of ones.
Yes.
It cannot be. It cannot have a preimage because the image always is just 1.
But it's not a valid row then.
Yes, yes. But by definition, a valid row is something that you can extend downwards. So you cannot expect a valid row not to be extendable downwards.
So we don't have...
But what I'm saying is that not all rows are valid. Not all rows are valid is the same as not all rows appear are extendable downwards, and it's the same as the cellular automaton is not surjective. Okay?
So it's not a valid cellular automaton then.
Well, it can be interesting for some other purposes, but if you look at the set of bi-infinite sequences, you may have some things that this subshift, the two-dimensional subshift, loses some information from the cellular automaton. Loses all the temporary information. So I've just inverted this notation. I don't know if it's clear. The two-dimensional uniform
Yeah.
population is only once. Okay? It's a bit weird. I don't think I will use it again because it's two-dimensional.
Well, it's understandable, so it's all right.
But, okay, this is very trivial, but imagine that you have an example of something a little less trivial. For example, with 3. So maybe I write 0 if maybe I write 1 if they are all equal to 1. And 0 otherwise. So, just a quick proof that it's not surjective. A cellular automaton is surjective if and only if every finite pattern admits preimage by parallel application of F.
Which application?
So, local root F can be extended. We already saw it for homomorphisms that you can define it could be, let's say that you add 2R and it gives you a word. So example, if it's 2R plus K, and it gives you a word of length K. This is trivial. It's really what I did here, for example. If I have a finite word, I have an int made by my cellular automaton, which is just a little smaller, okay? Etc. And if this map is surjective, then capital F is also surjective. Okay, exercise, and so to prove that F is not, this F here is not surjective, we just need to show one example of pattern which has no preimage. So you're happy to have come here because you have more exercises. Because we will stop now, but I will give you an example of pattern and you will check that it's. So, for example,
1, 0, 1.
Yes, very
It
good.
has no bridge.
It's called an orphan.
Can you spell it? Orphan.
Orphan.
Oh, okay.
Preimage. And using this as an exercise also, you will describe me what XF looks like. and what tau of xf looks like. Well, you will describe both at the same time, but it can help also to tau of xf is not the full shift, because you know that if for every configuration where you will have 1, 0, 1, you cannot extend it downwards. So we can describe what tau of xf. To describe it, you can try many things and see what's going on. It's interesting. Okay. So were there other questions on other exercises?
I have a lot of questions, but
So the last two, I think the last two.
how do you prove that it is aperiodic?
Mhm.
So we have no matter which
So-
substitution we have. How do we prove that there is aperiodic?
Suppose there is a period, and suppose that this period is bigger. So you take the definition of the substitutive subshift, and at some point every pattern bigger than the period should be inside the image of some letter. And then you will get to a contradiction by using the primitivity of the. By the way, did you have a question about? You started to speak about algebraic geometry that you.
Yeah, it was some similarities, some ideas similar to basic constructions of ideals. Like, for example, when we define SFT, we define some set that is prohibited to occur. In geometry, in algebraic geometry, in similar way, there is an ideal that has some primitive, some generators that in some way they are also prohibited, and there are also notions of like minimals, maximals.
So there is a notion. What you're saying is quite interesting. There is a general notion of closure space. I'm not very sure that it applies to what you're saying, but it applies to subshifts and also to finitely generated, to groups, to countable groups. And when you forbid a pattern in a subshift, it corresponds to giving a relation in the group. And you can derive like this, forbidding things, what is forbidden, what are bigger patterns which are forbidden by small patterns and things like that. Maybe it's similar to what you were saying also. Closure space is a very theoretical notion, and by the way, many computational results that are true in the theory of subshifts actually have a counterpart in the theory of finitely generated groups, and both can be expressed as something about closure space. So it would be interesting to know if what you're saying enters this framework also. Good question. What does the poll say?
Let me check.
Because I have answers by email also.